My name is Filip Švrček. I'm from Olomouc, Czech Republic. I am a university teacher in Olomouc, and I participate at the project dealing with Mathematica. Our goal is to implement this tool into our teaching lessons at our faculty. So a little bit general to motivation. It's enough or more? There are some problems with mathematics fields of study in Czech Republic. There is a decrease of number of students in these fields of study, and we would like to improve that trend from the last years. Most of young people find mathematics boring and difficult. They are not motivated to go to study these fields, and of course in future we can await the strengthening of these problems. So what can we do with that? I think that the solution is let us make mathematics more interesting, for example with Mathematica. What I would like to present to you is using Mathematica with some problems related to summing positive numbers, I can say. It will be a rather easy example for you, or a couple of easy examples for you, but I find it interesting to use in lessons of Mathematica, I don't know, at high schools or where you want to. So maybe that the resolution is too big. Yeah. First sum which I would like to present or show is the sum of well-known sum of the first n positive numbers. We have always plenty of possibilities how to speak with our students. Of course, we can say this sum is equal to 1/2 times n plus 1, and say remember it, and it's important to you. But I don't know if this is, yeah, that's not good. I prefer to speak about reasons why is it so, and that's what I would like to show you. So if we take, for example, some clever book or Mathematica software and let it compute the result, yeah, we obtain the expectable result output. What is more interesting is to show, let's make it maybe not so big. Yeah, if we look at this picture, we can see the first summand of our sum, but 2 times. Go to next step, and what we can see is the second summand, and also it is included 2 times. Third step, third summand, and so on and so on. Clearly visible from this picture is that our sum after n steps. So our sum must be equal to the number of 2 times the number of our balls or circles. And what is the number? Yeah, it is number of step times number of step plus 1. So if we divide it by 2, we can obtain our result. It was easy. Go on and our second example is the sum of the first n odd positive numbers. Again, we can take our software and let it compute the result. The result is square of n, but more interesting is again this picture. If we look at it, we can see the first month, but 4 times. The second step, in the second step, we add the second month, but also 4 times. Yeah, after repeating this n times, whatever we want, we get the result, or we can see that our sum is equal to 1/4 of number of these balls on the picture. And again, what is this number? In the step n, for example, this is step 3, and the side of the square which we have here is equal to 2 times 3, 2 times n. So yeah, the number of the balls on the picture is 2 times n squared, but we must divide it by 4 if we want to obtain our sum. So that's the reason why is the result such as it is. Further, we can take sum of first n squares. The result is a little bit more difficult, and yeah, the following picture helps us to find out why is it so. What is on the first picture? This is the first square, but 2 times. It is for comparison, and look at the second step. We add the second summand. This is this is square of 2. And what is square of 2? It is 2 times 2. So there are 2 possibilities how to interpret it. So the third step, square of the 3, and fourth, 5th step, and so on and so on. What follows from these 2 pictures is the fact that our sum is representable as other sum, namely the sum of, I can make it bigger, the double sum, which is built from the inner sum of some sums which are visible on the picture, which were visible on the picture. I can go back. I can go back, but Yeah, here is the picture. So we can sum the squares, or we can sum our squares by the lines. So this is the second interpretation of our sum, and let us check Mathematica. Let us check Mathematica what is the sum, what is the inner sum. If we let it compute, we get such a result, and the sum above is returnable in such a way as you can see now. And if we rewrite the right side of the sum once more, we get the following result. And from that result we can obtain our result which we have in the first output. Go on to the sum of the first n cubes. The sum of the first n cubes is equal to that, but why is it so? If we take such a picture done by manipulate command in Mathematica, similarly as the previous ones, we can see the first cube on the picture, but 4 times. This is the second step when we add second summand, that means 2 to the 3, but again 4 times. In the third step we add 3 to the 3 and so on, and it's clear that our sum must be equal to the area of this square. And in the step n, the square is the side of the square is of the length n times n plus n, and we must square it to obtain the result, and also divide it divide by 3, and that's the result which we have in the first output, if you can see it. And the final sum which I want to present to you is the sum of the product of 2 consecutive integers. Again, we can let Mathematica compute the result. That's it. And more interesting way to obtain this result is look at these 2 pictures. The blue ones are our members of the sum, or the summands, and we can go step by step. This is first step. I will explain what the yellow rectangles means. We can make it bigger. So this is second step. The blue ones are first 2 summands of our sum, 1 times 2 and 2 times 3 rectangles of those lengths. sides of those lengths, and we add the yellow rectangles above them to get one rectangle. And there are two ways how to interpret the areas of the yellow ones. If we go by the lines in each step, we can see that there is the sum of the first n integers in each line. Yeah, this is represented by the yellow rectangles in the line. We know from the first example that this sum is equal to 1/2 times n plus 1 in each step. So what we have here is one big rectangle, which is of area equal to 3/2 of our sum, and this area or area of this rectangle is expressible in second way or in a different way. If we look at the vertical side, its length is n plus 2 in each step, and the horizontal side is of the length equals to the sum of the first n positive numbers. So it is 1/2 times n plus 1. And if we divide it or multiply it with 2/3, we obtain the result which we expect. So that's all what I wanted to say to you. Thank you.